Beneath the glittering surface of the ocean lies another world, a world without sunlight, without warmth, without mercy. At 1,000 meters below the surface, light begins to disappear. By 4,000 meters, it is gone entirely. What remains is an endless blackness, silent, crushing, and cold. The pressure here is unimaginable, more than 400 times greater than at sea level, enough to collapse steel like paper. And yet, life thrives. But it does not thrive the way we expect. Down here, evolution plays by different rules. Creatures that should be small grow to impossible sizes. A shrimp becomes the length of your forearm. A jellyfish expands wider than a house. And somewhere in the abyss, a squid grows long enough to rival a school bus. This phenomenon has a name: deep-sea gigantism. For over a century, scientists have documented this strange pattern. Animals living in extreme depths often grow far larger than their shallow water relatives. But why? Why would the harshest environment on Earth produce giants? Is it the freezing temperatures, slowing metabolism, and stretching lifespans? Is it the crushing pressure, reshaping biology at a cellular level? Is it the darkness, driving evolutionary arms races we can barely comprehend? Or is it something deeper, something written into the fundamental rules of survival when life is pushed to its absolute limits? Today, we descend into the abyss, not just to witness these giants, but to understand the forces that sculpted them. Let's begin with what we know. Deep-sea gigantism is not myth. It is not exaggeration. It is a documented biological pattern, observed across multiple groups of animals living below 1,000 meters. One of the most famous examples is the giant isopod. Imagine a common pill bug, the tiny crustacean that curls into a ball in your garden. Now imagine that same creature, the size of a small dog. The giant isopod, Bathynomus giganteus, can grow up to 50 centimeters long and weigh over a kilogram. Encased in thick armored plates, it crawls slowly across the abyssal plains, feeding on dead whales, fish, and anything else that drifts down from the world above. It is a scavenger built like a tank, and it is only the beginning. Off the coast of Japan lives another titan, the Japanese spider crab. With legs stretching nearly 4 meters from claw to claw, it holds the record for the largest leg span of any arthropod on Earth. Its body seems almost fragile compared to its enormous limbs, which move slowly and deliberately across the seafloor, like an ancient machine assembled from bone and shell. In the deep ocean, survival is measured in moments, one successful catch, or weeks of hunger. And for many creatures of the abyss, size may be the difference between the two. Take amphipods, small shrimp-like crustaceans that in shallow coastal waters rarely grow longer than a fingernail. Insignificant, fragile, almost invisible. But descend nearly 11,000 meters into the Mariana Trench, and those same creatures transform. Here, some species stretch beyond 30 centimeters, longer than a standard ruler. In the deepest canyon on Earth, they gather in swarms, patrolling the trench floor for the rare gift of falling organic debris. A dead fish, a drifting carcass, a fragment of life from the sunlit world above. In the abyss, nothing is wasted. Even jellyfish follow this rule of enlargement. Far below, the surface drifts Tiburonia gran rojo, the so-called big red jelly. Its bell can exceed a meter across. Unlike the delicate tentacled jellies of shallow seas, this one carries thick, muscular feeding arms instead. It floats like a crimson lantern in the darkness, slow, deliberate, almost alien. Then there is deep steria, a jelly so rare that encounters are counted on one hand. Its body forms a vast, translucent dome, thin as silk, rippling like fabric underwater. It has no trailing tentacles. Instead, it engulfs prey by collapsing its bell inward, trapping victims inside its living curtain. Illuminated by submersible lights, it appears almost spectral, a drifting apparition in a world without light. And in perhaps the most extreme deep sea habitats of all, near hydrothermal vents, where seawater meets magma-heated rock, another kind of giant emerges, tube worms. Riftia pachyptyla can grow longer than 2 meters, taller than many humans if stood upright. Yet these giants possess no mouth, no stomach, no digestive tract at all. Instead, they host colonies of bacteria inside their bodies. Those bacteria convert toxic chemicals from vent fluids, hydrogen sulfide and methane, into usable energy. The worms do not hunt. They farm life within themselves. Here, gigantism is not about predation. It is about partnership. So why does the deep ocean repeatedly favor large bodies? The answer begins not with biology, but with physics. In the abyss, temperatures hover just above freezing, often around 2 to 4 degrees Celsius. Cold changes everything. At low temperatures, the chemical reactions inside cells slow down. Metabolism decreases. Growth becomes gradual. Movement becomes deliberate. For most animals, that might seem like a disadvantage, but in a place where food can vanish for months, burning energy slowly is survival. A slower metabolism means fewer calories required, fewer risks taken, longer endurance between meals. In the deep sea, patience is power. Cold water also holds more dissolved oxygen than warm water, and oxygen is the currency of life. Large bodies demand more oxygen to fuel their tissues. In warm tropical seas, oxygen dissolves less efficiently, limiting how large many organisms can grow before their own metabolism becomes unsustainable. But in the frigid depths, oxygen is abundant. Cells can breathe more easily, tissues can expand, mass can increase without suffocation. Then there is pressure. At 4,000 meters below the surface, the ocean exerts more than 400 atmospheres of force. It is a weight almost impossible to imagine, pressing inward from every direction. For humans, it would be catastrophic. For deep sea organisms, it is simply home. Perhaps evolution in the abyss follows rules we are only beginning to understand. Perhaps size is not merely an adaptation, but an experiment, an outcome of life stretching itself to the edge of possibility. And in the deepest trenches of Earth, possibility has very few limits. There is another idea scientists often point to when explaining size in cold environments. It's known as Bergmann's rule. Across many species, from mammals to birds, individuals living in colder climates tend to grow larger than those in warmer regions. Why? Because larger bodies retain heat more efficiently. As an organism increases in size, its volume grows faster than its surface area. And with less surface exposed relative to its mass, heat escapes more slowly. In the frozen abyss, even a small advantage in energy retention could mean survival. But temperature alone cannot explain everything. To truly understand deep sea gigantism, we must look at something even more fundamental: food, or rather, the absence of it. The deep ocean is often described as a desert, not a desert of sand, but a desert of nutrients. At the surface, sunlight fuels photosynthesis. Phytoplankton bloom in vast clouds. Tiny fish consume them. Larger fish consume the smaller ones. Energy moves quickly, abundantly, constantly. But descend below 1,000 meters, and the sun's influence ends. No light, no plants, no continuous source of fresh energy. The deep depends on what falls. Scientists call it marine snow, a slow, silent snowfall of organic debris drifting down from the surface world. Fragments of plankton, microscopic waste, tiny flakes of decaying tissue. From above, it may seem like a steady rain, but by the time it reaches the abyss, most of it has already been eaten.